Right. So communication. So what I'm going to say first is this is from the specific booklet that you can get online. It's free and it's available. A-level science application booklet physics. So it's for the 9702 syllabus. It's basically written by the Cambridge examiner themselves. So this is not an exhaustive authoritative resource. This is actually a slightly old resource back from 2009, but it pretty much covers most of the things you need to know. But the best place to read from is obviously the textbook itself. This just does a good job at explaining all of this very concisely. So yes, I personally prefer using this. So what I'm going to do is I'm not going to read through the stuff. I'll leave the reading bit for you, but I'll just explain every bit of the stuff. So, but because you guys are A2, you'll have to take the responsibility of reading through all of this. I'll just tell you each one a little by little. Okay, let's begin. I'll go a little fast, so you guys will have to follow me. If anyone feels like I'm going too fast, please feel free to ask me to slow down a little bit, all right? So let's start. So the concept of communication basically is when two people talk to each other, right? So there's a problem with the direct method of communication. That is, obviously it's limited distance. You can't have more than one person speaking at the same time. You can't choose between people to listen to when you have a lot of noise and stuff, or a lot of people talking. It's really difficult. And also, it's not a good way to broadcast. You can't, there might be noise and stuff disturbing the communication method. So we overcome some of these by using basically a loudspeaker connected to a microphone. Basically, this is the stuff we use for those big processions or those big meetings where you have someone speaking into a microphone and the speakers all around the place, or pretty much a simplified version of what happens at a concert. So basically, this shows what? That you can talk through a certain method and communicate using wire pairs, and then you're going to get sound on the other end. Now, the thing with this method is it's really good at allowing people to communicate, but there's one major problem with it. It's the same issue again. You can listen to only one person at a time, and also there's a limited range. There's a finite distance that this can cover, and along the wires the signal becomes weaker and weaker. This is called attenuation. We'll get to that soon. So then you had a bunch of people who I think over 100 years ago, I'm not exactly sure about the dates, but we had a bunch of people. What they did is they figured out radio communication. So what happened is they took the signals, basically the speaking, they converted into electrical signals, which were oscillations going up and down a cable. So oscillations of charged particles creates electromagnetic radiation. So that sort of radiation happened, caused the emission of electromagnetic waves, which got picked up, which traveled along a certain distance and got picked up by another antenna, which took them in and caused oscillations again. So they started moving up and down, up and down, and up and down. So they used that, amplified that signal, turned it into a signal, and then audio, and a person could hear it. So this was also pretty cool. It was pretty good actually, but there are certain limitations with this also. One of the major limitations is, so when we talk within the audible range of 20 hertz to 20 kilohertz. So again, this is a range difference of 1000. So that would mean the antenna has to have a difference in length by 1000 to be able to pick up all of the signals efficiently. So which means it's not an efficient way to use antennas. And another problem again is if we have one guy with this and then another guy and another guy and another guy having the same setup, all broadcasting at the same frequency, then this antenna and the amplifier will pick up and amplify all of those signals simultaneously. So you're just going to listen to a lot of people arguing on radio from different radio stations. So yes, that's basically what they talk about here, that these are certain issues that we need to deal with, and the best way to deal with is by creating what we call modulation. So modulation is basically when we take the wave, we add it into another wave, and we figure out what's the result of it. Basically we send it as a variation of that. So there's basically two types of modulation. So what we do is we take a carrier wave. A carrier wave is basically the wave which carries the information itself. So this is a wave which doesn't have any sort of information on it. It's just a constant, undisturbed sort of wave. So this is what they call an unmodulated carrier. The signal, the information will piggyback on this wave. So fluctuations in this will happen depending on this. And that is basically the concept of modulation. So if you don't modulate, you just have this. All right, so what we're going to do is we're going to add this information into this wave. But there's different ways of adding it. One way of adding it would be we represent a change in amplitude of the modulated wave by using this signal. So basically as the value increases here, we show that the amplitude increases. Here the value decreases, so we show the amplitude decreases, and then it increases here again, increases. So basically an increase and a decrease and an increase again. So based on that, we have this. which is amplitude modulation. So based on amplitude modulation, you have an amplitude which goes from a maximum, then a minimum, and then a maximum again. So they ask this a lot. What is amplitude modulation's definition? So it's basically. Maqsad, can you tell me amplitude modulation? Come on, man.
So when amplitude is modulated with reference to the
you can't use modulation in modulation definition. Give me a minute or Google.
No, give me a word for it. Modulation.
It is varied in synchrony or changed in synchrony with the. What is changed in synchrony? The amplitude of the carrier wave is varied in synchrony to the displacement. Or actually the displacement of the carrier wave is varied in synchrony to the displacement of the information signal. So that's amplitude modulation. You have the definition in this book. It's really nicely written, so you can just follow that. All right. And the other way of modulating is basically, instead of playing with the amplitude, you can play with the frequency. So if you do play with the frequency, we call it obviously frequency modulation. And as you can see, high frequency, low frequency, high frequency. And that's exactly what we see here. High frequency basically representing a high positive value, low frequency representing a low value, and then again another high frequency. So high, low, high. And can you tell me frequency modulation's definition, Maqsood?
Is when the frequency is varied in synchrony.
Yes, to the
frequency of
wrong displacement of the information signal. It's always the displacement of the. You made a mistake that a lot of people do, so that's why I'm not going to strangle you tonight. But basically, it represents the displacement of the information signal, right? The frequency varies in synchrony to the displacement of the information signal, and that is basically frequency modulation. So yes, that's that. Let's move on. Well, please read this stuff, guys, because it's really important. So yes, amplitude modulation, if we just read the sentence, amplitude of the carrier wave is made to vary in synchrony with the displacement. So yes, it's actually amplitude. Amplitude of the carrier wave is made to vary in synchrony with the displacement of the information signal, blah, 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 blah. And if it's frequency modulation, the frequency of the carrier wave is made to vary in synchrony with the displacement of the information signal. There you go. Really easy, really straightforward. So next concept up is the concept of bandwidth. So what happens is, if you just transmit an unmodulated carrier wave, it just sends this one frequency. Say this is, 100 kilohertz. So what you're going to get is you're going to get a signal of just 100 kilohertz. So say this is 10 kilohertz. So what's going to happen is, this will vary. This signal's amplitude will vary with a 10 kilohertz frequency. Basically, it will go to maximum to minimum to maximum again, 10,000 times per second. So what this does is it creates sidebands. So basically it creates a signal, the original signal at 100 kilohertz. And what's going to happen is at 10 kilohertz minus and 10 kilohertz plus, you're going to get two sidebands. So basically this is like when you're tuning into a radio and you slowly tune into it and you slowly start listening to the signal, but it still has a lot of static, right? And then eventually that's when you're passing the sidebands, right? So for this case, if it's 100 kilohertz, this would be at 90 kilohertz because it's FC minus A, frequency of the carrier minus the audio signal, and it's going to be FC plus A. So that's frequency of the carrier wave plus the information signal. So you're going to hear a sideband at 90 kilohertz, and you're going to hear another sideband at 110 kilohertz. And the actual signal itself is going to be at 100 kilohertz. That's why we always tune into exactly the frequency of the carrier wave. But around it, you do hear these sidebands. Now, interestingly, what happens is when you're talking, you're not creating an information signal of the same exact frequency, right? You're having a range of frequencies. So that basically means what? That these sidebands will move back and forth to side. So if you're talking at a high pitch frequency, they move far away. If you're talking at a low pitch frequency, they move towards each other. So they move back and forth, right? And the difference between them is obviously going to be FC plus minus FA. So yes, where FA is the frequency of the audio signal. So this range is called the bandwidth, and it's constantly varying if your signal has a varying frequency. So this is basically what they talk about here. Basically, this is a conversation having different frequencies, and it results in a spread of the bandwidth. All right, then they have this big paragraph here on page 30, and it's this nice explanation as to why exactly are the differences and the advantages and disadvantages of amplitude modulation and frequency modulation. So I'll just say these really concise in a nutshell so that you know what to read. For example, amplitude modulation picks up a lot of noise, right? So like, for example, from a storm, that's why you hear crackles on the radio when you're listening to AM signals, or from a motorbike because they emit radio waves similar to the frequency and amplitude modulation sometimes. So what happens is amplitude modulation ends up picking up a lot of noise, so the quality of the signal is poorer. While FM, because it's frequency modulations, it's really difficult to make it match up with some sort of interference, because you have to have a changing frequency that it matches up. So what happens is frequency modulation is pretty much significantly more resistant to picking up noise, and hence it's better in that manner. Second paragraph is about how the amplitude modulation has a bandwidth of 4.5 kilohertz. Basically, audible frequency goes up to 20 kilohertz. So you have low quality sound. You don't get the higher pitch sounds because it's not so useful. However, for frequency modulation, what happens is you can have really, really high frequencies. So that basically means you can send really high quality signals along FM signals, FM wavebands. And then these are the disadvantages of AM versus FM. Basically, it picks up more noise, AM, and it's also lower in quality because it has lower frequencies. Now, FM also has some disadvantages. Number one, you need more bandwidth, right? So basically, an FM signal requires around 200 kilohertz, while an AM signal station requires only 9 kilohertz. So you can fit in a lot more AM stations. For example, they did this maths here to show in the low waveband that you can fit in 30 AM stations, while you can only fit in one FM station. So that's why FM stations have really high frequencies compared to AM stations. So that's an advantage of using AM. You can have more stations at lower frequencies. AM also has another significant advantage. That's why, the really global ones that are all AM, is because their wavelengths are really long, they don't lose energy so fast. Basically, longer wavelength signals lose energy much less. So those have huge ranges, while FM is much less, just a few kilometers, 30 kilometers specifically here. That's why, AM stations in Bangladesh, there's going to be only one AM station, which is like Bangladesh Betar. And they do operate on FM signals also, but if they were to operate as they used to previously on AM, one station would be able to cover the entire country. However, for FM, you'd have one station in each city. That's why, all the other major radio stations that we listen to now, they have one station in Dhaka, they have another station in Chittagong, they have another station in Sylhet. So the reason that is because their range is much less. Moving on, AM transmitters are also cheaper because the electronic parts of it are also much simpler, and FM stations are more expensive. The bandwidth is also more, which also increases the cost of FM stations. Right, these are the advantages and disadvantages of AM and FM stations. All right, there we go. This is on page 30 of the book, the application booklet, as it's written here, and as it's written here, it's issued in 2009. All right, but it's a decent guide to follow. All right, guys, I'll just go really quick with the cables and the different channels of communication, basically, and we'll wrap up there. I've been talking and talking and talking.
Yeah, I'm fine.
Yes, I need some water too. Anyway, let's go ahead from here. So there's different ways in which you can send signals. So there's wire pairs. We'll talk about wire pairs. They're really bad. And then there's coaxial cables. This is an image of a coaxial cable. Basically, that's the cable that we use for our televisions, which sometimes may get struck by lightning, which may destroy televisions, right?
No.
I apparently heard that someone's television got damaged today.
Yes, mine.
Oh, that's so unfortunate. Then we have radio links, and then we have microwave links, and at the end we have optic fibers. Right, so I'll just quickly breeze through these one by one. So wire pairs are literally, as the name says, two wires in a pair. So wire pairs are horrible when it comes to communication. Bangladesh landlines used to use it once upon a time. Thick wire pairs, do you remember them?
I could hear other people talk.
Yeah, that's exactly.
And then I told my dad, I think someone rigged into our line and then our other line, and turns out, I was kind of stupid.
Yeah, that's basically this thing which is called crosstalk. So crosstalk is when you have a lot of wire pairs placed side by side, right? So what happens is the electromagnetic, basically the electrons moving up and down one of the cables causes electromagnetic radiation, which causes the other one to pick it up like an antenna. So this thing is actually called crosstalk or cross-linking, and it basically means that it has really bad security. It's awful, it's horrible, it's horrible, it's horrible. If you have anything else to use, then use that. And it also has a really low bandwidth, and also it attenuates the signal really fast, which means the signal strength drops really quickly over very little distance. So we use this over really short distances, like, if you have a speaker, on one floor and someone listening on the floor underneath. So that's basically when we use these sort of cables. So yes. That's wire pairs. It's a horrible thing, and they used to use it for telegraphs and Morse code and stuff. So yeah, that's not exactly the best thing to use. Yeah. So after that, a slightly better variation of that is coaxial cables. That's basically the cables that we use for television and get struck by lightning. So basically what happens with those is struck by lightning.
Yeah.
Oh, you missed out on that? All right. So basically on those what we do is we have the wire pair set up, but in a slightly different variation. You have one thick wire going through the middle, and you have a copper mesh which is around the two wires. So what basically happens here is that the copper wire carries the current, and the mesh on the outside carries the current back. It's basically like an earthing, but also shields the copper wire. So basically this is slightly better. It gives a little more security, but not really like, the ultimate in security. So yes, it minimizes the amount of crosstalk we get, it minimizes the amount of noise that it picks up, and also it has a slightly higher bandwidth, and it can carry much more information because of having a high bandwidth. And that's the advantage of using coaxial cables.
Expensive though. Expensive though.
Well, slightly more expensive than wire pairs, yes, but it's worth it. Then we have basically radio links. Radio links are within a certain frequency. This is where we use our AM and FM signals. So they are usually within the range of 30 kilohertz to 3 gigahertz. And they're pretty much all right. And they can cover a large amount of distance. For example, we have they're broken down into different types of waves. So see, for example, here we have like, stuff like surface waves. Surface waves can go up to 1,000 kilometers. So basically, you could say as long as you can see it and stuff. Interestingly, there's this thing called the sky waves. What they do is they bounce between the atmosphere and the ground as around the earth, so like, bump, 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 bump. And that's really cool because you can transfer information throughout the entire planet using sky waves. So like, BBC World, for example, a long time ago, they used sky waves. So you could communicate anywhere using sky waves. Pretty cool stuff. And then you have space waves, which are basically really high frequency, so they can actually penetrate the ionosphere and go to satellites. So it's a radio wave that we use, but we don't use it pretty much for satellite communication all the time. We also use microwaves there. But they're line of sight, basically. If you can directly see it, then you can transmit to them. All right, so that's pretty much it. Then you have these things. You don't really need to know the VHF, UHF, and all of that. If you want to, you can, but it's not an essential thing. They don't really ask this. All right, moving on, then we can talk about microwave links. So microwave links are pretty cool. They work from 3 gigahertz to 30 gigahertz. They have these little dishes, like, from one building to another. If you want to communicate, usually we use these microwave signals, and they're emitted by parabolic dishes. So the transmitter and the receiver are these little round things here. These dishes are just to be reflectors and collectors. They do not act as antennas. So basically signals sent to the other end, it picks it up, and then transmitter and receiver. So they're really good at covering short distances. And basically they are able to actually send a lot of information over a short distance, and they're pretty good. Bandwidth microwaves out of gigahertz. Consequently, microwaves have very large capacity for carrying information. So sometimes you have internet connections from one building to another using microwave connections. However, for terrestrial use, the range of transmission is limited to line of sight. For long distance transmissions, many repeater stations are required. And eventually we have the best of the best optic fibers. These are basically really thin things, strings of glass. So basically these things they use total internal reflection, and they can send a huge amount of information, which is limited to the technology that we use. These values have been updated because these are almost a decade old, but basically what they show is how the signal can be transmitted at really high speeds. And what this shows is basically you can send information over a huge distance very easily. So we have a long list of all the advantages of using fiber optics. So basically they have really high bandwidth. Read this part, by the way. It's about how it's limited by the switching on and off system that we have, but we can transfer it at much higher rates. So you have really high bandwidths, you have relatively small, you have really high bandwidths, and the signal losses is really small. And basically you can have long cables without amplifiers in the middle, and they're really cheap, they're really lightweight, they're very flexible, they're extremely secure because it's total internal reflection, so crosstalk doesn't happen, almost no crosstalk. Electromagnetic waves doesn't interfere with them, and also they don't have to get disturbed by anything. And yeah, basically they can send information really rapidly using in digital format, which is pretty ideal for what we do. So yes, that's pretty much it for communication channels. And I guess that concludes today's discussion. We talked a lot about this, and we talked about AM and FM. Hopefully next class we'll talk a little bit about the rest of communication.